So we have been looking at the eigenvalues and eigenfunctions for the simple harmonic oscillator. And in the last class, we obtained the energy spectrum of eigenvalues for the simple harmonic oscillator, and it turned out that they could be enumerated by some integer n, which could take values 0, 1, 2, 3, 4, etc. And the corresponding energy was half h cross omega into n plus half. So we had a discrete set of energy levels for the simple harmonic oscillator. We also worked out the corresponding eigenfunctions. So and they turned out to be some polynomial into e to the power minus xi square by 2, and the ground state was some constant into e to the power minus xi square by 2, which was psi 0, the ground state, the lowest energy possible. We also calculated the first excited state, which turned out to be some constant into xi into e to the power minus xi square by 2. So let me now show you these functions. So the ground state, the lowest energy state of the simple harmonic oscillator, is a Gaussian, and on the computer screen you can see the wave function plotted as a function of xi, where xi is the distance x along the x-axis, the position scaled with some x naught, which is some position, some dimension, some number of dimension length which appears in the problem. So this is the ground state wave function of the simple harmonic oscillator. It is a Gaussian. Let me also show you the first excited state, which is given by this. It is just xi into the Gaussian wave blanket. So the green curve over here shows you the wave function corresponding to the first excited state. If you notice, the ground state does not intersect the x-axis, does not pass through the value 0 anywhere, whereas the first excited state passes through the value 0 once at x equal to 0. So each of these intersections with y equal to 0, the intersection with the x-axis, is called a node. And the first excited state, as you can see, has got one node. We also calculated the second excited state, which we found was given by some constant into 1 minus 2x squared into e to the power 1 minus 2 xi squared into e to the power minus xi square by 2. So this was the second excited state. So let me now show you the second excited state of the waveform corresponding to the second excited state. So the blue curve over here shows you the wave function corresponding to the second excited state. So as you can see, it has got two nodes. It crosses the x-axis twice, and it is a general feature as you keep on looking at the wave functions corresponding to the higher and higher excited states. The number of nodes corresponds to the value of n over here. So if I am looking at the nth excited state, I will have n nodes in the wave function. Let me now discuss a few general features of this wave function of the simple harmonic oscillator. The simple harmonic oscillator corresponds to a particle moving along one dimension. The situation we have been considering is a particle moving along the x-axis. So what are the various observables that we have for this particle? So some of the observables that we have so we can write down three observables corresponding to this particle. One is x, another is p, and then we have the energy of the particle E. Now the question arises that suppose so we have been looking at the possible values of the energy. So we have been studying the possible values that the energy can have. And the question arises, suppose I just tell you the energy of a particle, does it uniquely fix the wave function? And we have found that it does, because the energy we found can take values h cross omega n plus half and correspond. So the energy has got discrete values, that's what we found, and corresponding to each value of n, we have a unique wave function psi n x. So if I fix the energy, the wave function is uniquely fixed. And we have looked at the wave functions for n equal to 0, n equal to 1, n equal to 2, and you can construct higher order polynomials and get the wave functions corresponding to higher values of n. Once you tell me the energy, the wave function is uniquely fixed. Once the wave function is uniquely fixed, you can predict what value of p you expect to get, or what value of x you expect to get, what is the variance or expectation value of delta p squared, etc., by just taking suitable expectation values. So if you tell me the wave function by just telling me what is the value of energy corresponding to the particle, everything else is fully defined. Let us compare this situation to a free particle. For a free particle, we also have x, p, and e. Suppose for a free particle you tell me the energy. Is the wave function uniquely defined, fixed for that? For a free particle, the answer is no, because I have two possibilities. One possibility is exponential I p x by h cross, and another possibility is exponential minus I p x by h cross. So this corresponds to a particle with momentum p, and this corresponds to a particle with momentum minus p. Both of these will have the same value of energy, because the Hamiltonian operator is p square by 2m. For a free particle, and if this acts on these two wave functions, it will give me the same value for the energy. I will have the same eigenvalue for the energy, but these two wave functions are different. So if I make a measurement of momentum, the expectation value of momentum is going to be different for this, or the position is going to be different. So these are two different wave functions which correspond to the same value of energy. So telling the value of energy does not uniquely fix the wave function. You have to actually work with the eigenvalues of the momentum. If you tell me the eigenvalues of the momentum operator, that uniquely fixes the wave function. So this is a situation where we have a degeneracy. This is what is known as degeneracy. And for a free particle, eigenfunctions of H or Hamiltonian or energy are degenerate. There is more than one eigenfunction corresponding to a particular eigenvalue, and so this is what is known as degeneracy. And if I specify just the value of the energy for a particle, it doesn't uniquely fix the eigenfunction. So if you have degeneracy, then the situation is a little complicated. You can always choose a combination of observables which will break the degeneracy. In this case, if just the momentum itself breaks the degeneracy, because if I tell you the eigenvalue of momentum, the wave function is uniquely fixed. Going back to the simple harmonic oscillator, the eigenfunctions or the eigenvalues corresponding to energy are non-degenerate, and for each value of the energy, we have a unique wave function. This is a generic feature by and large of bound states. Okay. So this is one feature, one very important feature of the simple harmonic oscillator, that the energy eigenvalues uniquely fix the wave function. The second feature of the simple harmonic oscillator wave function is as follows. To study the second feature, let me introduce what is known as the parity operator. So what the parity operator does, there is something called the parity operator. It operates on a wave function psi x, and it gives me the wave function psi of minus x. So this is what is known as a parity transformation. I have changed, so psi of x going to psi of minus x is what the parity operator does. Now there can be wave functions, or in general there can be functions which are odd. What is an odd function? So an odd function transforms in the following way under the parity transformation. Psi of x is equal to psi of minus x. This is the definition of the parity operator. And if this is equal to minus psi of x, such a function is called odd. So this wave function is said to have odd parity. You can also have functions of even parity. So a function of even parity behaves as follows. If the parity operator acts on it, then this is equal to psi minus x, and it remains unchanged. So wave functions could be functions of odd parity. For example, odd, a function with odd parity is sine x. It is quite obvious, if the parity operator acts on this, I get minus sine x, so it picks up a minus sign under the action of the parity operator. I have even functions cos x, and I have functions with no well-defined parity. No well-defined, no parity basically, neither odd nor even. For example, cos x plus sin x. This has no well-defined parity. So if psi x is equal to cos x plus psi x, there is no relation between psi x and psi minus x. It has got no well-defined parity. Now it is a property, if you look at the solutions, if you look at the wave functions, you will see, if you look at psi 0, you will see, which corresponds to n equal to 0, which is even, you will see that the wave function also is of even parity. So this is even. So the wave functions corresponding to even values of n are of even parity, and the wave functions corresponding to odd values of n are of odd parity. So let me put it down again here. For simple harmonic oscillator, psi nx, the eigen functions of the simple harmonic oscillator problem have got well-defined, has particular parity. Okay, they are all eigenfunctions of the parity operator also, and if n is odd, then psi n is odd. If n is even, psi n is even. This is an important property of the simple harmonic oscillator problem. Now let us look at the general eigenfunction. So the general eigenfunction psi for any arbitrary n, we have seen it should be some polynomial of order n, maximum order n, multiplied by e to the power minus xi square by 2. So we can write psi nx as a product of some normalization constant c of n into a polynomial. This polynomial h subscript n xi is a polynomial called the Hermite polynomial, whose properties we shall come to. So the nth energy state of a simple harmonic oscillator has a wave function which is some constant into the nth Hermite polynomial into exponential minus xi square by 2, a Gaussian. And the Hermite polynomial of order n is a polynomial which has got maximum degree xi to the power of n, and if n is even, then only the even terms are there. If n is odd, only the odd terms are there. And this polynomial is called the Hermite polynomial. I have written down a few of the Hermite polynomials. You can work out these Hermite polynomials by using the recursion relation which we had worked out in the last class. So the coefficients of the different terms in the polynomial can be worked out using the recursion relation we had worked out in the last class. And a few of the Hermite polynomials are written here. So h naught, the 0th Hermite polynomial, is just 1. The first Hermite polynomial is 2 into xi. The second Hermite polynomial is minus 2 plus 4 xi squared. So you see there is a slight difference. If you compare it with the solutions we had obtained, you will notice that there is a factor of 2 coming over here in the definition of the Hermite polynomial, and there is another factor coming over here in the definition of the Hermite polynomial. We had calculated the second excited state, which should be some constant into the Hermite polynomial h2 into e to the power minus xi square by 2, and h2 we see is minus 2 plus 4 xi square, which is nothing but the same thing multiplied by a number. Okay, and then we have h3 over here. So the highest order power of xi is xi cube now, and we also have h4. And you can work out all the other higher Hermite polynomials. So the question arises, how do we go about working out the higher order Hermite polynomials? So let us now spend a little time looking at some properties of the Hermite polynomial, because the Hermite polynomials are important for the simple harmonic oscillator wave function. And if you want to do any calculation with the simple harmonic oscillator wave function, then you will have to use the Hermite polynomials. So the Hermite polynomials are defined in such a way so that the coefficient of xi to the power of n in the nth Hermite polynomial hn is 2 to the power n. So the polynomial is defined so that this coefficient of the highest power of n is 2 to the power n. And you can use the recursion relations to work out the coefficients of all the lower powers of n. So here the coefficient of the highest power is fixed in the Hermite polynomial. And the Hermite polynomial satisfies the differential equation, which was the differential equation we had obtained for the simple harmonic oscillator function, from the simple harmonic oscillator function problem, which is h double prime, where the prime indicates derivative with respect to xi. So hn double prime minus 2 into xi into h prime plus 2 into n h is equal to 0. So this is the equation satisfied by the nth order Hermite polynomial. And you note that n appears in the equation itself, and it is here the coefficient of hn. So the solutions of these equations, with the condition that the coefficient of xi to the power n, the highest power which appears, should be 2n, will give you the Hermite polynomial. Now suppose we take the derivative of this equation. So if we take the derivative of this equation, then we obtain this, which is what is written here. So if you take the first derivative, you get this equation, which has got the third derivative of h. And here, if you take the derivative, then if you differentiate this, you still have h prime, which is this term over here. And if you differentiate h, then you will get h double prime. And if you differentiate this, you will get h prime over here. So what you are left with is this equation. Now let us call h prime n to be some function f. Then this equation can be written as f double prime minus 2 xi f prime. So this term over here is minus 2 xi f prime, and we can combine this term and this term, these two terms, and write it as plus 2 into n minus 1 into f is equal to 0. Now let us look at this equation. This equation we see is just the same as this equation, except that here we have n minus 1 instead of n. So what does this tell us? This tells us that f is equal to, is a solution of this equation with the n minus 1 coming over instead of n, which means that f, which is actually h prime, is proportional to h n minus 1, because this is the same equation as the equation for the Hermite polynomial, just that we have n minus 1 over here. So it tells us that f is proportional to h n minus 1. The n minus 1th, so the derivative of the nth Hermite polynomial is proportional to the n minus 1th order Hermite polynomial. Now how do we get the coefficient relating this to this? We know that so to get the coefficient, we have to equate, to get the proportionality, constant of proportionality, we have to equate the coefficient of the highest power of xi, which appears over here and over here. The highest power of xi which appears on both the sides is xi to the power of n minus 1. Because this has the highest power here is xi to the power of n. If you differentiate, you get xi to the power of n minus 1. And this is the Hermite polynomial of order n minus 1. So the highest power of xi is xi to the power of n minus 1. Now the Hermite polynomials are defined so that the coefficient of the highest power is 2 to the power n. So in Hn, the coefficient of xi n is 2 to the power n. If you differentiate it, then you get n into xi n minus 1. So the coefficient of xi to the power of n minus 1 in this term is 2 to the power n, which was already there, and n which you get on differentiating xi to the power n. So the 2 to the power n into n is the coefficient of the highest power of xi in this term. The coefficient of the highest power of xi in this term is 2 to the power of n minus 1. So we have to multiply this whole thing by 2n to make it equal to this, which tells us that h prime n, so the derivative of the nth order Hermite polynomial is equal to 2n times the n minus 1th order Hermite polynomial. So we have obtained the constant of proportionality between these two. So we have the equation now that h prime n is equal to 2n into h n minus 1. So let us now keep this equation in mind and go ahead further. So we proceed by defining a function of two variables. We had these Hermite polynomials which were a function of xi. Now we proceed to define another function, capital F s comma xi. This is what is called the generating function of the Hermite polynomials. So instead of obtaining different expressions for these polynomials, you may suddenly want to write down the 10th excited state of the simple harmonic oscillator. Now then, if you want to actually do that by using the recursion relation, you will have to find out all the recursion coefficients of all the different powers of xi which will appear there. So to avoid having to do that, there are certain mathematical things called generating functions which will allow you to obtain these coefficients in a simpler way. And we want to obtain the generating function for the Hermite polynomial. The generating function for the Hermite polynomial is a function of two variables. There is a variable s and there is the variable xi. The variable xi which is there in the Hermite definition of the Hermite polynomial appears as the argument of the Hermite polynomial. This generating function is obtained by summing up all the Hermite polynomials. The Hermite polynomial of order n is multiplied by s to the power of n. So s is some new argument which is introduced. So the Hermite polynomial of order n is multiplied by s to the power of n, and the whole thing is divided by n factorial. And we add up this whole thing for different values of n going from 0 to infinity, and you get this generating function. So once you know this generating function, if you expand this generating function in a Taylor series in S, the coefficients of each of the powers of S will give you the corresponding Hermite polynomial. Now let us see what is the generating function for the Hermite polynomials. So the way we go about finding out the generating function is that we first differentiate this whole thing with respect to xi. If you differentiate the generating function with respect to xi appears on the right hand side only in the Hermite polynomial. So you have h prime xi, and we just calculated what is h prime xi. This is nothing but 2 into n into h n minus 1. So we have differentiated the nth order Hermite polynomial, and we get the n minus 1th order Hermite polynomial here, and we get an extra factor of 2n. So putting in that, we get the derivative of the generating function. Also note that the sum now runs from 1 to infinity instead of 0 to infinity, because the 0th order Hermite polynomial is a constant. If you differentiate that, it doesn't give you anything. So n now goes from 1 to infinity. Now, if you change the variable n to, so if you now, instead of n, you use n minus 1 to be n, then the new n which you have will go from 0 to infinity, and you will have 2s outside, because this will now become, so okay, so now we are, instead of the old n which we had, we are replacing by a new variable which we call n minus 1. Wherever n minus 1 appeared in the old expression, you replace it by n, and this n and n factorial here cancel out, one factor of n. So what you have now is n minus 1 factorial. So this whole expression here can be replaced by a sum from 0 to infinity, and we have one extra factor of s and this factor 2 which can be taken out. So finally we are left with a partial differential equation that del f del xi is equal to 2s into f itself. Okay, so we have this partial differential equation for f. And the problem which we have now is to actually solve this partial differential equation. So how do we go about solving this partial differential equation? This is very simple. You can just bring this f over here and take the d xi over there, because it only involves derivatives in xi. S is a constant as far as integration or differentiation with respect to xi is concerned. So the solution is something like ln f is equal to 2s into xi plus some constant of integration. which finally gives you f as a function of s and xi is equal to f s xi equal to 0. So this is some constant as far as the derivative with respect to xi is concerned into e to the power 2 xi s. So this is obtained by just integrating this with respect to xi, where this is the constant of integration as far as integration with respect to xi is concerned. So we now have an unknown constant over here into e to the power 2s into xi. And this unknown constant is some function of s. So as far as this integration is concerned, it is just a constant. Now we want to find out what is this constant. Yes, does somebody have a question? No. Okay. So we can work out what this f s comma 0 is. So this function can be easily obtained by putting 0 into this Hermite polynomial here, and this is equal to the sum n running from 0 to infinity h the n 0. So it has the Hermite polynomials evaluated at xi equal to 0 into s to the power of n by n factorial. So we also now know how to calculate this constant of integration which has appeared here. For that we require to know the Hermite polynomials at xi equal to 0. Once we have this, then we can sum this up and we know the generating function. So now let us evaluate the Hermite polynomials at xi equal to 0. The odd Hermite polynomials, the lowest power of xi which appears is 1. And then by using the recursion relations, you can get the coefficients of all the higher powers, and you have xi to the power 3, xi to the power 5, etc. If you set xi equal to 0, then it is very obvious that the Hermite polynomial disappears. So none of the odd terms contribute. All the odd Hermite polynomials are 0 for xi equal to 0. Now let us look at the even Hermite polynomials. So the even Hermite polynomials have got C0 plus C2 xi square, etc. When we set xi equal to 0, then we are left with C naught. So this is the first thing. So for any Hermite polynomial, the value at xi equal to 0 is C naught. Now all the Hermite polynomials are defined so that Cn, so for the nth order nth Hermite polynomial, Cn is equal to 2 to the power n. So the C0 which appears in the different Hermite polynomials is going to be different, because C0 has to be chosen in such a way so that the highest coefficient Cn which appears should be equal to 2 to the power of n. So for the for the 0th Hermite polynomial H0, we have C0 is 1. In H2, for example, in the second order Hermite polynomial, C0 will be a different number, because C2 will be equal to 2. So we have to work out what is C0 in the second Hermite polynomial. So let us work out what is C0 in the nth order Hermite polynomial. We know that so we know the relation between Cm minus 2 and Cm. This is just the recursion relation between the coefficients which I have written down again. And what is the recursion relation? It relates Cm minus 2 to Cm. And Cm minus 2 is equal to m into m minus 1 into divided by 2 into m minus 2 minus n into Cm. The n here refers to the Hermite polynomial we are considering. It comes from this Hn. So we are looking at a fixed value of n, and we want to find out what is C0 for that. So this can also be written as minus m into m minus 1 divided by 2 n minus 2 minus m into Cm. And we also know that Cn is equal to 2 to the power n. So let us calculate Cn minus 2. We know that Cn is equal to 2 to the power n. Let us work our way backwards. In this case, we have to work our way backwards. We are given Cn. We have to find out Cn minus 2, n minus 4, n minus 6, all the way to 0. So how much is Cn minus 2? This is equal to, so let us plug in. So we have to put in n here, and n here. So if you put in n here, and n here, what we are left with is minus n into n minus 1 by 2 into 2, which I can write as minus 1 minus n factorial by n minus 2 factorial into 2 to the power of n minus 2. So we find that Cn minus 2 is equal to minus n factorial by n minus 2 factorial 2 to the power of n minus 2. So Cn was 2 to the power n, Cn minus 2 is 2 to the power of n minus 2 with some coefficient, which is what is given here. Now let us use this to calculate Cn minus 4. So what is the relation between Cn minus 4 and Cn minus 2? So we have to now put n minus 2 instead of m. So wherever m appears here, we have to put n minus 2, and that gives us Cn minus 4 is equal to, the minus sign comes over here, and we have n minus 4, n minus 3. If you put n minus 2 over here instead of m, and then we have a 2 over here, and this term n minus 2 minus m gives us 4 when you put n minus 2, n plus 2 minus m. So we have a 4 in the denominator, and we have Cn minus 2. Now let us put in Cn minus 2, which we have just calculated. So let us put this into this, and what we have is the two minus signs disappear, we have a plus, and then we have n minus 1, n minus 2, n minus 3, and we have 2 to the power n, which is what we had here, divided by 2 into 4, which is what comes from here, and we had 2 into 2 from here itself. So this is Cn minus 4, which we can write as Cn minus 4 is equal to n factorial by n minus 4 factorial. This whole thing here is n factorial by n minus 4 factorial. And then I have this term here gives 1 factor of 2, and the other factors of 2 I can absorb into this, which gives me 2 to the power of n minus 4. Okay. So we see that Cn minus 4 is equal to n factorial divided by n minus 4 factorial 1 by 2 into 2 to the power of n minus 4. You can work your way down and then write down the general term Cn minus m, and if you do it, it turns out that this is equal to minus 1 to the power of m by 2. This is because every time you put a m here, every time you go down 2 steps, you pick up a minus sign. So it keeps on flipping between minus, plus, which gives you minus 1 to the power of m by 2. And then you have n factorial divided by n minus m factorial, which we saw was the pattern coming here. And we have 2 to the power of n minus m, which you also saw was the pattern emerging here. This 2 over here, if you calculate n minus 6, you will get a 6 here also. And you calculate n minus 8, you will get, so the term, this 2 over here basically will, if you keep on calculating the higher and higher terms, what you will find you get is 2 to the power of m by 2 into m by 2 factorial. This is the term which you will get, which will basically come from this combination of these two. in the recursion relation. So finally, we find that Cn minus m is equal to this whole thing over here. And we want to calculate C0. So to calculate C0, we have to set m equal to n. If we set n equal to m, what we are left with is as follows. These two exactly cancel out. We have 1 to minus 1 to the power of n by 2. This 2 to the power of 0 is what we get here. We have 2 to the power of n by 2 coming from here and n by 2 factorial. So this is what is C0. You can go through this yourself and verify. And the last step I have not done explicitly, but you can actually check that if you use the recursion relation, you can get the fact that C0 is equal to this, provided Cn is 2 to the power of n. So using this C0, we find that, okay, so the Hermite, so the nth Hermite polynomial at 0 is also equal to C0. So the nth Hermite polynomial at xi equal to 0 is minus 1 to the power of n by 2, 2 to the power of n by 2, n by 2 factorial. So this is what is the nth Hermite polynomial at xi equal to 0, which is nothing but just C0. So we have to use this expression to calculate the constant of integration which we wanted to evaluate, which is this. So we have to use the expression which we just calculated in this. This is what we wanted to evaluate, the generating function f as a function of s at xi equal to 0. And we have to do this sum. So putting in the result of the calculation which we have just calculated, we've completed, we get f s0, which was the constant of integration in the differential equation for the generating function, is equal to minus 1 to the power of n by 2, 2 to the power of n by 2, n by 2 factorial, which one, and then we have s to the power of n. The n factorial which was there has cancelled out with the n factorial which appeared in the h of 0. The n factorial which was there here, the n factorial here has basically cancelled out with the n factorial which appeared over here. That is the only thing. So we are left with this. And this is only valid for even n. For odd n, the Hermite polynomial is 0 at n xi equal to 0. So we have to do this sum only for even n. And you can see that this is equal to the Taylor expansion of the following function, e to the power minus s squared. If you do a Taylor expansion of this, what you get is this. You can just match the coefficients and you will get this. Okay. So using this, plugging in the constant of integration, we find that the generating function is nothing but e to the power 2 xi s. So we had solved this differential equation for the generating function, and the generating function turned out to be the constant of integration f s0 into e to the power 2 xi s. We have now solved for this, and we found that this was nothing but e to the power minus s squared. So putting it in, we get the generating function to be e to the power 2 xi s minus s squared, which we can also write as e to the power xi squared minus xi minus s whole squared. Now how do we go about using the generating function? Suppose I want the nth order Hermite polynomial. what I have to do is I have to differentiate the generating function with respect to s n times. That will get rid of s to the power of n. All the lower terms will drop out. I set s equal to 0, all the higher terms will drop out, and what I will be left with is h to the power of n. So if I want the nth order Hermite polynomial, I have to differentiate the generating function. Well, one way is to just do a Taylor expansion of the generating function in powers of s, and the coefficient of s to the power n is the nth divided by factorial n will give me the nth order Hermite polynomial. Or I could go about by differentiating the generating function n times with respect to xi, and that's then set s equal to 0. This will also give me the nth order Hermite polynomial. This derivative I can write in a slightly different way also. This derivative I can, if you look at the generating function, you will see that I can take this xi e to the power xi square outside of this derivative. So I can take this e to the power xi square outside of the derivative, which is what has been done here. So e to the power xi square has been taken outside. In addition, what remains then is a function of xi minus s. If I have a function of xi minus s, differentiating it with respect to s is the same as differentiating it with respect to xi, except that I have to put a minus sign. So this derivative with respect to s I can also replace with a derivative with respect to xi, but I get a minus sign. So I can take this outside the derivative with respect to s. What remains is a function of s minus xi. So derivative with respect to s is equal to a derivative with respect to xi with a minus sign. So there are n derivatives here. So I have minus 1 to the power of n, and I have n derivatives with respect to xi. If I set s equal to 0, then I get this. So this is an alternate expression, same expression for the Hermite polynomial, just written in a different way. So this is an alternate expression for the Hermite polynomial. And you may use whichever one you find convenient to find out the nth order Hermite polynomial. So what have we, so let me finish here today. Before completing, let me just recapitulate what we have done. So what we have done is, I have told you that the nth, the wave function corresponding to the nth eigenvalue of energy can be written as some normalization coefficient, which is still to be determined, into the nth order Hermite polynomial into a Gaussian. And I have also obtained the generating function for the Hermite polynomials, which is this. In the next class, we shall obtain the normalization coefficients, and we shall use the generating function to study some properties of the simple harmonic oscillator.